Along gross anatomy, like have bigger features of the heart, how propagation goes from the SA node down to the ventricles. Today we're going to dig a little deeper and understand how individual cardiac myocytes generate the action potential and how that controls the heart rhythm. So we're not going to get into the SA node per se, but we're going to think about how atrial and ventricular myocytes contract. And if we look at it, over here on the right, you can see different types of action potentials, right? So last class we spent quite a bit of time talking about the SA node and how it oscillates. If we put an electrode on the inside of an atrial myocyte and recorded the potential relative to the extracellular space, you get a much more triangular looking action potential. And if you put this cell in a dish, it wouldn't beat on its own. It would just sit there unless you stimulated it electrically. And if you continue, remember that the Purkinje fibers are responsible for the rapid spread of the action potential through the ventricles. You can see that they have a different shape altogether. And then finally you have the ventricular action potential, and it's the longest. So, and that's because it needs to bring in the most calcium. So the point is, the point is that the cells each have specialized action potentials that are tailored to the function of those cells. So the signaling that controls their contraction is unique and necessary for the function that those cells function. All right, so let's talk a little bit about how we think about excitation of cardiac myocytes. So I think people who were in QP last semester probably had this, but we'll review it. And also for people who are kind of jumping into QP2, and then we'll take QP1 later. So you can think of a cell membrane as a circuit model. And so I always found this concept particularly fascinating, that you can think of the cell membrane as a capacitor. Capacitor separates charge, just like the cell membrane separates charge, right? So you have some charges on one side, other charges on the other side, and the low dielectric, the hydrophobicity of the membrane keeps those charges separate. So you can think of the cell membrane as a capacitor. There are proteins called ion channels that selectively allow sodium or potassium or chloride ions to go back and forth across the membrane. So you can think of those as resistors. And those resistors, the conductance or the resistance of those resistors depends on voltage. So they're variable resistors, which is why we have a line kind of going through diagonal. And finally, we have a difference in concentrations of sodium or potassium on either side of the membrane. So you have the most sodium outside the cell and less sodium inside the cell. So you have about 140 millimolar sodium extracellularly and 10 millimolar sodium intracellularly. It's opposite for the potassium. So for potassium, you have about 100 millimolar intracellularly and about 4 to 5 millimolar extracellularly. So if you remember your Nernst potential, probably from QP1 or from chemistry, it's going to be determined by the difference in those concentrations. And so the value that we assign to the battery is simply determined by the Nernst potential. And so one way you can think about this is if you cut yourself, I mean, the first thing you do is put your finger in your mouth, right? And it's salty. And that's because there's sodium chloride in there. But if you scrape your knuckles, you release a lot of intracellular milieu. And if you taste that, it's a lot more metallic. So the metallic taste is from the high potassium that you get when you scrape your knuckles. If you have a bloody cut, then that's going to be more salty. So if you haven't done that, maybe we can try it next time. Or we can make it a homework. Can we add that to the lab? Yeah. So timing-wise, you remember what your neuronal action potential looks like. when sodium current opens, remember you have more sodium outside. The sodium ions want to run into the cell. So you're bringing positive charges into the cell, and that's going to make the membrane potential go up. So this isn't current, this is conductance. So this is how many sodium channels are open. So sodium channels open, that allows the positively charged sodium ions to come into the cell, and that brings the membrane potential up. Once the membrane potential comes up, the potassium channel's open, and remember now you have more potassium inside the cell, and it starts to leave. So you have positive charges leaving, and that brings the membrane potential back down to rest. And so the peak potentials and the resting potentials are largely determined by the reversal potentials of the channel, right? So how high you go is going to be determined by the sodium channel reversal potential, or ENA. On the other hand, how low you go, or where you go during rest, is going to be determined by the potassium channel nurse potential. So questions about that? Is that a good review? Do you remember from last semester now? For the most part? Okay. All right, so what do we have to think about for the heart? So neurons release neurotransmitters. That's a calcium-driven process. Heart cells contract. And so the main reason why, heart cells contract is because calcium comes in. So calcium is a critical component that allows myocytes to contract. And I'm assuming you guys got this in bio, right? The cross-bridge cycling? Yeah, for the most part. So we're not going to spend a ton of time on it. That was a prereq. But to remind you, calcium moves the filament, the thin filament over, and that exposes the binding site to allow for cross-bridge cycling. And then ATP and ADP get hydrolyzed so that there's a conformational change, and then it keeps repeating over and over again so that the myocyte contracts. So the point is that calcium is a critical component of the action potential, right? So the point of an action potential is to allow calcium to come into the cell and tell it to contract. The whole point of the action potential is to bring calcium in. Once calcium comes in, cell contracts, and then action potential ends. Calcium goes back where it came from, and the myocyte relaxes. So that's what we're trying to get to, is how does the action potential bring in calcium to tell the myocyte to contract? So this is the atrial action potential. As we mentioned, they're fairly triangular, right? So it goes up, and then it has a fairly shallow slope down to rest. So you can see how a triangle would fit over there. And so we talked about the neuronal action potential, right? So sodium brings it up, potassium brings it back down. For the atrial action potential, again, sodium is very important for initiating the action potential. So sodium channels open around minus 60 millivolts. So if, let's say it's next to the SA node cell, the SA node cell comes up, current travels through the gap junctions that we talked about last class, and then that brings the membrane potential of the atrial myocyte up to minus 60. At minus 60, sodium channels start to open. So you get this huge influx of sodium current. You get this very rapid upstroke. Around 40 millivolts, let's say around here, minus 40 millivolts, calcium channels start to open. So the initial upstroke, that shot up, is due to the sodium current, but that opens up the calcium channels. Now calcium starts coming into the cell, and they'll release more calcium to tell the myocyte to contract. One kind of funny feature, and it's still a little bit debated as to why this happens, is a notch. So if you look at the waveform here, it shoots up due to sodium and calcium, and then it comes back down, and then it bounces a little bit. So that bounce down is opening of the transient outward potassium current. So potassium channel opens, out go the potassium charges, but then it inactivates. So the transient outward current doesn't stay open, and it doesn't keep repolarizing the action potential. It just brings it down a little bit. And so the idea behind this is that it's going to affect the timing of the contraction just a little bit. And so you have distribution of ITO throughout the wall, the atrioventricular wall, and that'll synchronize the timing of those myocytes. So it just kind of delays it a little bit, the contraction, and that allows, when you don't necessarily have the whole wall all the way across getting excited at the same time, it kind of synchronizes the push, so you get more efficient feed. A unique aspect of the atriomyocyte is the ultra-rapid potassium current. And it doesn't look very rapid there, but as you can see, these lines are fairly steep. And so what they mean by ultra-rapid is that it opens and closes very quickly. So the dynamics of opening and closing are very quick. That's one of the reasons why you have a triangular shape. Finally, the current that's most important for bringing the atriomyocyte back to rest is the rapid component of the delayed rectifier, or IKR. So IKR, you can see it's increasing over time, and when it wins over, so there's kind of a battle between the sodium current, the sodium currents don't turn all the way off, and the calcium current, and they're bringing charges inside, right? When IKR finally brings more charges out, it wins, and the action potential comes back down to its resting state. Finally, the most important component for maintaining the resting potential, so right here around minus 80 to 90 millivolts, is IK1. So IK1 stays open. If we look back to the Hodgkin-Huxley model, give me a second. There was this kind of undefined component called the leak current that's actually due to IK1. So in the Hodgkin-Huxley model, the leak current's maintaining the resting potential. In atriomyocytes, the inward rectifier IK1 is responsible. So there are some differences between atrial and ventricular myocytes. So as we said, the ventricular myocyte's a little longer. So it's got to bring in more calcium. You get longer contraction in the ventricle. And so you also get a longer action potential and more calcium coming in. Again, you get depolarization by the fast sodium channel. There is a component of ITO. It's most notable in the epicardial cells. So those are the cells that are right on the outer surface of the heart. The fast component of the delayed rectifier is still important for bringing the action potential back down to rest, but there's a second component called IKS that's also important. So that's the slow component of the delayed rectifier. IKS tends to be most important during beta-adrenergic stimulation. So if the heart has to beat harder, more calcium comes in, so you need more repolarizing currents to fight it, to bring it back down to the resting state. So it's fairly minor component of the action potential here. If you add adrenaline, it'll increase a lot. And then that'll help counter the increase in calcium that you get when the heart's beating harder. And again, you have the inward rectifier currents that are important for maintaining the resting potential. Okay, so that's kind of the overview of which currents are important for creating the atrial and ventricular action potentials. And you can see that they all kind of interact with each other, right? So, for example, the sodium current is going to open the calcium current. Calcium currents are going to keep the potential high, which allows IKS and IKR to open. IKR and IKS opening are going to cause the calcium channels to deactivate, and all of these are going to interact through the membrane potential and also through the intracellular ion concentration. And so making predictions in terms of what's going to happen to the myocardial electrophysiology is very challenging, because it's like you poke one thing and 4 different things happen because they're all talking to each other. And so this has been an area where computational models have been really helpful in helping people understand what's going on. And so the lab that you'll do this afternoon is to use one of those models and to start understanding why that works and why that's helpful. And the home of these models has traditionally been in B&E. So most of the work that's done on these types of models is done in biomedical engineering. So what do we think about when we look at action potentials? What are the properties that we want to think about? Well, one is the minimum diastolic potential. So how low does the membrane potential go before it fires? And this is usually around minus 80 millivolts. The next thing we want to think about is what's the threshold for action potential firing? So basically, when are your sodium channels opening, which is about minus 60 millivolts. The next important part is DVDT max. So how quickly is the membrane potential changing? Any idea what that's going to depend on? DVDT max?
Quickly the ions make it through the channels.
Right, which is charge over time, right? Ions through channels. Right, peak sodium current, right? So how quickly the ions are getting through the channels is going to be the current, right? So if we look at the peak, sodium current, then that's going to correspond to DVDT max. So this peak sodium current does not correspond to the peak, right? So the membrane potential changes, the derivative of the membrane potential is equal to the current, not the membrane potential. The DVDT max is actually going to be the peak sodium current. The other important component is the action potential duration. So how long is the action potential? And right, so our action potential duration is going to be different for an atrial myocyte, which is pretty triangular, than ventricular myocyte. And so usually what people do is they measure APD 90. And so that's 90% repolarization. So you take the difference between the peak and the minimum diastolic potential, and that's 100%. And when you get to 90% of that back down, that's APD 90. So that's one way you can characterize it. So you can characterize an action potential by saying, okay, what's APD 90? What's APD 50? What's APD 30? Right? So some action potentials might have the same APD 90, but if it's more triangular, it's going to have a different APD 30.
So I guess like APD 10 or something would be near the top. And then you have, because it goes up, you have 2 points that correspond to that. So how
Yeah.
do you know
That changes depending on what paper you may read. So usually, that's a really good question. So usually people will do at where it starts to come down. So this is usually the peak people think about, and then they think about the last return, right? So if you have a really steep notch, they'll go all the way over here before they start doing those percent. That's a really good question. And some people will take this peak instead of that peak. Other questions? Okay. Oh, finally the cycle length. So the cycle length is the time between sequential beats, right? So 60 beats per minute has a cycle length of 1,000 milliseconds. Right? So just so we have all the terms. Finally, I want to tell you about the different phases of the action potential. So phase 0 is the rapid rise. Phase 1 is that initial return due to the transient outward current. Phase 3 is the end of repolarization, and phase 4 is at rest. Right? So initial shot up is 0. That little dip back is phase 1. Phase 2 repolarization is during the plateau, and the end stages are phases 3 and 4. All right, so calcium cycling. So now we know that we open calcium channels, but not enough calcium comes through to cause the kind of contraction that you need. So it's the calcium that comes through calcium channels, right here is CAD 1.2, that's the L-type calcium channel in the ventricular myocytes, won't really trigger contraction. You need a huge release that's stored intracellularly. And so that intracellular store is carried in the sarcoplasmic reticulum. So you have a big compartment here where calcium concentration is really high. And the change is almost 1,000 times from resting all the way to the top. So calcium comes in, and it causes the ryanodine receptor to open. So again, you have a lot more calcium inside the sarcoplasmic reticulum. Calcium comes in, opens up the ryanodine receptor, out goes the calcium into the cell, and tells the cross bridges to contract. Because you're bringing in calcium through the L-type calcium channels, you need a mechanism to send it back out, right? So you can imagine if you kept spacing a cell, right, your myocytes are beating once a second. Every single time you're bringing a little calcium in. So you need a way to send it out. And that's accomplished through the sodium-calcium exchanger. So the sodium-calcium exchanger relies on the sodium gradient, right? So you said there's a sodium gradient of 140 outside and 10 inside. And it brings 3 sodiums in while it sends 1 calcium out. And then the sodium-potassium pump maintains the sodium and potassium concentration. There's also a secondary mechanism to extrude calcium, and that's the plasma membrane calcium pump, PMCA, and that uses ATP. So it hydrolyzes ATP and sends out a calcium, which is kind of an expensive way to do it compared to the exchanger. So we talked about ryanodine receptors releasing intracellular calcium. It also needs a way back into the sarcoplasmic reticulum, and that's carried by SERCA2A. So SERCA2A is a protein that grabs calcium from the inside of the cell and sends it back into the sarcoplasmic reticulum. Now the way first pass thinking about this, especially when you see a diagram like this, is you think that there's this big bag of calcium, and it's somewhere by the membrane. In comes the calcium from the outside, and out goes the calcium from the sarcoplasmic reticulum. In reality, it's a lot more sophisticated, I think, in terms of the SR is kind of a distributed network. So you can think about it as a compartment, but it's kind of spread all the way throughout. And that's so that when the calcium comes in, you get this huge release that's distributed across all the sarcomeres, and you get a uniform contraction. So you don't necessarily want to have calcium come in and have a local release, because just the sarcomeres right around that local release are going to contract. You want a synchronized release all across the cell, so you get a unified movement, and you get maximum efficiency in the contraction, right? So if the different parts of the cell are all going to contract at different times, it's not going to be efficient, right? It could be like you get a contraction here, and then there. They all move at once, you're going to get a lot more force. Okay, so let's talk about how we make a model. So now I think we kind of understand the basic components, right? So you have a circuit model that describes the current. You have calcium cycling that needs to describe how calcium moves through the SR. You also have calcium affecting the current. And so we have to think exactly how we model that. And so the 1991 Luo-Rudy model was essentially designed to make a good Hodgkin-Huxley-like model of the cardiac myocyte. So the Hodgkin-Huxley model describes a lot of dynamics of the neuron really well. And so does the Luo-Rudy 1 model. It includes the sodium current, calcium current, and potassium currents. But remember, calcium is pretty essential for the behavior of a myocyte. And because calcium regulates the currents more in myocytes than it does in neurons, you need to start tracking the dynamics of the calcium. So in addition to saying, so in the Hodgkin-Huxley model, you have a fixed intracellular potassium. You have a fixed intracellular sodium. In a cardiac action potential model, it doesn't work that well if you hold the concentration fixed. So you need to have a dynamic calcium concentration to describe how those myocytes work. And so that's the famous 1994 model of the action potential. If you were around during winter break, you might have seen Yoram walking around the halls. He's in sabbatical in Oxford this year. He'll be back next year, though. So he's closing in on retiring, but he's still around, and he's a professor here. And it's a really well-known endeavor that his lab did to put together the Luo-Rudy model. So if you see him around, you can ask him about it. He'd love that. So one of the criticisms of these more detailed models is people have kind of a love-hate relationship with both of them. So if you use this earlier one, the 1991 version, people say, well, that's not very accurate because you're not tracking calcium concentration, and that's really important for describing myocyte dynamics. In contrast, if you use the 1994 version, you'll have 20 state variables, and you'll have close to 300 parameters. And then the more detailed models have thousands of parameters, and hundreds of state variables. And so you sacrifice the simplicity of the model and the ease of understanding the dynamics for more accuracy. And this is constantly the debate that goes on when people make models, is how complex do you make it? And so the answer is just complex enough to answer your question. But that's usually easier said than done. So usually what people want to do is a model, they can plug in their experimental data and see what's going on. And so that ideal is fairly difficult. All right, so what things do we have to think about now that we have a myocyte model? So we talked about the Hodgkin-Huxley model. If you guys put that together, right, with the Euler, you never put in the volume or the capacitance of you just set capacitance to a value, right? I think it's probably 1. But you never really had to think about the shape or the dimensions of a neuron when you did that. You just thought about the active dimension. But if you're going to keep track of intracellular ion concentration, you have currents coming in, now you have to think about how much volume you have, right? Because if you have a certain amount of calcium current and that's going to change the calcium concentration, you need to know what the volume of the myocyte is, so you know how much that's going to change. So now you have to start thinking about how big your myocyte is. And so lengthwise, it's about 100 micrometers, which is probably bigger than you thought, right? Like, here's a centimeter. It's about 1/10 of a centimeter. So if you look closely, if you're a little bit nearsighted, you can see cardiac myocyte pretty well if it's sitting in a dish. You won't see the details, but it's not hard to see that you have little myocytes in there. Across, it's about 11 micrometers, so they're pretty thin. So they tend to be kind of rectangular, and they're aligned along the fibers. So we talked about the fibers and how the gap junctions are on either end. So they're rectangular, and the gap junctions are on the short side. So the cell volume is fairly low. So it's 38 microliters, or less than that, 38 times 10 to the minus 6 microliters. And you can see that you have all these volumes. So you also have to think about what the volume of the SR is. So the SR is about 6% of the total cell volume. And then there's 2 parts of the sarcoplasmic reticulum. One's the network SR that's spread out over the whole cell to bring the calcium back in. And then you have the junctional SR, which is about half. And so the junctional SR is what releases the calcium. All right, so now that we know what our myocyte looks like, and we know that we need to create currents, right? So we have this variable resistor. So we need some way to start finding the parameters that describe the time and voltage-dependent dynamics of those currents, right? So the currents open as the potential goes up, and then they have a dynamic behavior as time continues, right? So if you start at a low potential, you'll get a little bit of opening. This is Hodgkin-Huxley sodium that they measure. And then as you go up, you get more and more sodium, and then it tends to close after you've held it up for a while, so it inactivates. So you have activation of the sodium current, and you have inactivation of the sodium current. In the Hodgkin-Huxley model, you have 2 different gates, right? You have m cubed, which determines the activation, and you have h, which determines inactivation. And if you look at the equations that describe m and h, they're voltage dependent. So the time dependence comes from these 2 differential equations. So dm dt is equal to some forward rate times the number of channels closed minus some reverse rate times the number of channels open. So this is your time dependent. It's going to depend on the rates. The rates, in turn, are going to depend on voltage. And these are the equations that describe the voltage dependence of the rates. So you have gates that are both time and voltage dependent. The rates describe the alphas and betas describe the voltage dependence of those rates. And so the question is how do you find 0.1, 25, and 10? And the answer is you do an experiment similar to Hodgkin and Huxley. So you measure the currents, and then you hold the potential constant. So you start at a low potential, and you raise the potential. And it's kind of like you're poking it, right? So you just add, it's a square pulse. It's what you do in every single engineering class, right? You do a square pulse, and you see what the response is. And so you keep going up to higher and higher potentials, and then you see what the dynamic response is, so that you can fit the rates, the voltage dependence of these rates. So one thing you can see here is that at lower potentials, the activation rate is slower than at higher potentials. So you would expect that you need a function that increases with respect to voltage as you keep increasing it. So the most, we'll talk about sodium channel protocols, especially because this is what's going to be on your homework. So a good time to pay attention. So a volt, yes?
Was that the last slide?
Yeah.
The different concentration, was that with the voltage clamp?
Yes. Yeah, so they're holding it at different potentials. And in the neuron for those early experiments, they just took out the potassium. And so this is what was left over. So it said this is sodium dependent, because it disappeared when they got rid of the sodium too. Other questions about this slide? Okay. All right, so now let's apply different potentials. So this is a current we recorded in our lab. And you can see that when you apply a lower potential, it opens partially and then it closes, it inactivates. And you get more and more current as the potential increases, and then it starts to kind of go back down. So why is the peak going back down? So this is the first pulse we recorded. This is the second one. And this is the third one. So any ideas on why that would happen? Why are you getting less current as you apply a higher potential? Like we said, the activation is increasing, right? It's getting faster. So why are we getting less current at a higher potential?
You're reaching the equilibrium potential of the channel.
Right. Yeah, so you're getting closer and closer to the reversal potential, right? So if we look back at our equations, maybe this is too long ago to remember, but GNA is equal to E minus ENA. So we had this little battery here, and as V gets closer to ENA, our potential is going to get smaller and smaller. So this is an important point that tends to confuse people, is why the conductance and current curves look different. So the first thing we want to do is kind of understand what the time dependence is, right? So if we look at this differential equations, these two differential equations, we can solve those analytically. They're just first order differential equations. And the analytical solution looks something like this. So m is equal to m infinity minus m0 times the exponential of minus t over tau m. So if we're looking at activation, we can look at this rate and we can start measuring tau m. So we can measure tau m as a function of voltage. So by looking at the time dependence, we can start getting the rate constant. And we can also get the rate constant or the time constant for each. The second thing that's important is the steady state value, right? So we know we're going to get an idea of what the taus are by looking at the time dependence of the traces, but now we have to think about where they're going to end up, right? So we need to find m infinity and h infinity. And those tend to be characterized experimentally. So when people want to understand how a sodium channel works, they tend to find the steady state activation and the steady state inactivation. So steady state activation is how many channels are going to open and stay open as a function of voltage. Steady state inactivation is how many of those channels are going to close. Because remember, we have two behaviors here, right? We have activation, which is opening. We have inactivation, which is closing back up. And if all the channels were inactivated to start, we'd never see any of them open, right? So there must be a voltage dependence to inactivation as well as to activation. So usually what people do is, because the sodium channels don't stay open, if you were looking at potassium channel, you just open it, you'd see where it ended up, and that would be your steady state. For sodium channels, we don't really have that luxury, right? Because they inactivate. So we don't really know exactly where they end up. So what people do is they make the assumption that the activation is at steady state when you get your peak sodium current. So they assume the channel's done activating at that peak, and then inactivation is much slower, and then it's going to take over after all the channels have opened. Now, that's a bit of a questionable assumption, but it's still helpful to plot out those measurements. It's just not bad. It's not a good idea to assume that that's true. So the IV curve, so IV is current against voltage, is plotted by taking the peaks of each of those currents and plotting them against the potential. And it looks something like this. So you see increased current. So sodium currents are going into the cell, so by convention they're negative. So you always see sodium current is going down, right? So you're getting more and more current, which means it's getting more and more negative. And then over here, it kind of tails off and goes the other way. And so again, that decrease in current is caused by the membrane, or the reversal potential, right? So the increase in current is caused by the channels opening and opening and opening, but then eventually the voltage is going to get closer and closer to the reversal potential, and it's going to start flowing the other way. So even though the channels are all the way. So then the current voltage curve is a little interesting, but probably what's more interesting is GNA, right? So for our model, it's pretty easy to model V minus ENA, right? But the hard part is getting GNA, right? So what we want to plot so that we can get M is GNA, and that's called the GV curve. And so the assignment that we have attached to the lab is you'll be using the Hund-Rudy model. And what I'm going to ask you to do is plot the GV curve for the Hund-Rudy model, and also the inactivation curve. So the activation curve here is going to simply be the current voltage relationship divided by the reversal potential, or the driving force, sorry. So V minus, we're going to divide out V minus ENA. So let's just write it out. So if our current is equal to GNA times V minus ENA, we can get GNA by dividing our current at each potential by V minus ENA. So we just divide out this. So this is the driving force. And we divide that out to get the GV curve. So if you look at this curve over here, this is a GV curve that reflects the IV curve. It's just with the driving force divided out. And you can see as the potential increases, the steady state conductance, the pseudo steady state conductance is increasing. Now the second thing we have to measure is the inactivation. So this is how many channels are closing as we increase the membrane potential. And that's a little bit more tricky, right? So why is that tricky? If we want to find the steady state. Well, what's the steady state? I mean, that's pretty easy, right? Like it's zero. There's no channels open at steady state, right? They're all closed. And so how are we going to measure steady state inactivation if just all the channels are closed? And so the reason why it's difficult to measure steady state inactivation is because inactivation is happening before the channel's open. So you're lifting the membrane potential, and before you're getting to the potential where the channels are opening, the inactivation is taking place. So this isn't going to be helpful for determining steady state inactivation. We need a different protocol. And so what people do for inactivation protocols is they apply potentials at different levels. So you start at very negative potentials, and supposedly here at minus 150, and that's usually fairly reasonable, you're not going to get any inactivation. And so you start at a really negative potential, you've totally relieved inactivation, and then you do a test pulse. So you measure how much current you get after a step, say to minus 20 millivolts. So you hold at minus 150, you step up to minus 20. Now you raise the membrane potential a little bit, and you see if you get any less current during that test pulse. So you have two parts of the protocol, right? So you have one pulse, so you start at a really low potential, say minus 150, and you step up to minus 120. And this pulse induces inactivation. Now we want to apply a second pulse. No channels have opened at minus 120, remember? So sodium channels open at minus 60. So we haven't opened any channels, we've just caused some inactivation. So now we're going to apply a really quick test pulse to see how many channels inactivated during our induction pulse. Now we step up here, minus 20, and we see how big our current is. And if we have any inactivation, we compare that to this one down here, right? And so if we have any inactivation, it's going to be a little smaller. So for the dotted line pulse, maybe we expect to see a current that looks something like this, right? If we step up to a higher potential, now maybe we expect to see a current that looks something like this. And so we take the difference of those peaks and we plot those against the graph. And then we keep going up to higher and higher potentials until finally we don't get any current. Right? So if we step up to say minus 70, we'll inactivate almost all of our sodium channels, or minus 60 even. Does that make sense? You're going to have to do it for your homework. So it's a good idea to ask questions if you don't understand. Yep.
Could you explain again what exactly causes the channels to inactivate?
That's a good question. So there was the structure of the sodium channel just came out, and the reason why everybody thought they inactivated for the last 40 years changed. And so it's essentially a hydrophobic docking of one of the intracellular linkers close to the pore, and it's kind of closing up the pore. But everybody basically thought it was this hydrophobic little triplet kind of coming in and blocking the pore, but it wasn't. It kind of bites next to there. And so the whole field just kind of got thrown into turmoil maybe 6 months ago. But we'll talk about that in a future lecture. But for now, we just need to know that as voltage increases, you get more and more inactivation. Yep.
Is that just as voltage increases or as the potential decreases?
But what do you mean?
I mean, because it seems like you're going from negative, like you're going closer to zero, not just that it's increasing, but you're going closer to zero.
Oh, so you're saying the magnitude?
Yeah.
So as it goes from negative to positive, so sodium channels are inactivated at 0. And if you add more potential, they won't uninactivate.
Okay. So at 0 or greater than 0 there?
Actually, I would say, if we look at this curve, where would you say? So this is the inactivation curve of wild type. So they're inactivated, where would you say they're inactivated above? Yeah, about minus 50, right? So at minus 50, so inactivation is the downgoing curve, right? So above minus 50, you've totally lost all of your sodium channels. So as you go up, you wouldn't see any current when you applied that test pulse anywhere above minus 50. All right, so one more protocol, right? So we can measure how fast the channels open by looking at the activation protocol. We can measure how fast they inactivate by looking at how fast these traces go back down, right? We need to understand how fast they recover from inactivation. Some people measure how fast they deactivate too, but usually it's too fast to really matter for these models. So that's one that's commonly omitted. It just has to be relatively fast. But we do really need to understand how quickly the channels come back from inactivation, because if they don't come back from inactivation, what's going to happen? Right, so you won't be able to get your next action potential. And that's really important for arrhythmias, right? So if your myocytes are constantly ready, if they're jittery, right? So if they're constantly firing, the heart's going to be a much more pro-arrhythmic substrate. So the timing of the ability and the timing of the myocytes to be ready to fire is really important for the heart's stability. And so you can see here in the wild type channel, this is a mutant that caused monkey T syndrome. Yeah. No, sorry, this probably caused Brugada syndrome. So this is a loss of function mutant that was pro-arrhythmic. You can see that the channel is much slower to recover than the wild type. So the protocol that we use to measure recovery from inactivation is similar. So the first pulse, we're going to induce an activation, right? And so, well, let's make this a little smaller. So we're going to induce an activation, and we're going to get a sodium current here, right? And that's going to inactivate. And now we're going to wait for a short amount of time and see if we can get any sodium current back. So if we wait for a very short amount of time, and then we apply a second pulse, we're not going to get any current, right? Because it hasn't recovered from an activation yet. So you can see right here, for this mutant, if you only wait 1 millisecond, you get about 1% of the current back. But if we wait for longer and longer times, we get more and more back. So if we do this longer hold at lower potentials, now we'd expect something like this. And so by measuring the peak as a function of the interpulse duration, we can start understanding what the time constant is for the recovery. And so which one of these do you think, which parameter is that going to affect the most?
Tau H.
Yep, exactly. So it's the time constant of the recovery from the inactivation. Okay. So questions about how to measure GV curves, inactivation curves, recovery from inactivation?
Can you go back to what, and can you draw like a similar voltage and current diagram for the inactivation test?
Oh, that was this one.
Yeah.
Oh, you mean right under it?
Yeah.
That's
Just like half
yeah,
an
yeah,
hour.
that's a good idea. All right, so for this one, at minus 120, we're not going to open any, right? Because we're not at minus 60 yet. And so we're going to get something like this. And you'll get a lot of current at minus 120. But now let's say we go up to, I don't know, minus 60. Now we're going to get a little blip here, right? We're going to open some channels, and then we're going to inactivate. And now we're just going to get a little blip over here. We'll get a very little bit of current that will be hard to see. And then we'll get a little blip of inactivation. So we'll get a lot fewer channels when we do the test pulse because we've inactivated them at minus 60. Right?
Okay. So the reason that we have no current for the minus 20 is because channels are not open.
Right.
They're not activated.
Well, so if
They're
we...
not inactivated either.
Okay, well, so let's say we did to minus 20. What would that look like? Right here.
There should be a flat line.
No, at this place, right here?
It'd be a loss. So you would have your almost maximum.
Yeah, exactly. You'd have a huge current, but then when you got over here, what would you expect? Yeah, flat
Nothing's
line.
because it's still the same.
Right, right. Yeah, so it's inactivated there. So usually we don't pay attention to this part of it because this is just telling us, this is just to induce an activation. What we're really interested when we do an inactivation protocol is what's happening when we're applying the test pulses.
Okay, so when you have your initial, and then you change the test pulse more frequently?
Yeah, yeah. So you're changing the potential of the test pulse, and then you're plotting the peak current against this test pulse potential. So that's giving you the amount of channels inactivated as a fraction, as a function of voltage. Okay. Other questions?
Why did you choose minus 20 as the test?
Because that's a huge, you get a huge amount of current there. So this is probably minus 20 right here. So you basically want to get as much as possible so you get your biggest signal. And that way, if you get this really tiny blip, you have a really big peak to compare to. That's a good question. Yep.
I'm really confused. Like, what exactly are you going to ask us to be able to do and understand?
All of it. No, so I want you to be able to build your own GV curves, your own inactivation curves. I want you to think about what happens when a GV curve shifts, right? So this is a T704M mutation. T704M is in white. So what happened here?
So we have to like translate that into something like that.
Well, one thing I want you to understand is, okay, what does that mean? What does a left-shifted GV curve mean? More inactivation? It's a GV curve though. GV is activation. So it's a left-shifted activation curve. Right. Yeah, so it's going to open earlier, right? You're going to start opening channels at more negative potential. So it's a gain-of-function mutation. And we haven't talked about it yet, but gain-of-function mutation cause something called the long QT syndrome. So if you get more current coming through the channel, you're going to get more depolarization, and that can be pro-arrhythmic. So we're going to talk about, maybe today, maybe next lecture, exactly how that happened. And then I want you to be able to build these curves. So I want you to be able to look at these traces and understand where those curves come from. Other questions? Yep.
So going back to the inactivation, we're comparing a single current response for just minus 20 compared to like a response after a stimulus has already happened.
We're comparing so this is your 1, and 0 is obviously 0. So whatever your response is at your most negative potential is your 1. And then you want to see how much it decreases as you increase the voltage. So the goal is to increase voltage and see how much inactivation is decreasing. And so ideally you want to set this potential low enough so that the second pulse doesn't change it. Right? So you really don't want to see a difference between minus 150 and minus 140. And so you can see that they were able to do this for both, and that's probably why they chose that, right? So minus 150, minus 130 are the same. So they know that they're at the top of the curve. It's not like they're going to go down to minus 180 and they're going to see a lot of channels that aren't inactivated. This is kind of the top. That's kind of why they choose such a negative potential. Right, let's continue. I feel like you'll learn the rest of it while you do the homework. This is probably not. So how do we put it all together? So we learned about fitting currents and getting the different kinetic parameters, that make the currents. And what we want to do is be able to put all these currents together to make an action potential. And we talked about this. The sodium current open at -60 activates the calcium current. Eventually, the potassium currents overcome the inlet current. Kind of one thing that's interesting to think about is why do you think that cells don't just use calcium to depolarize the action potential?
Sorry, can you repeat that?
Like why do they have, why is there a sodium current? Why couldn't you just use a calcium current that opens at -60?
Isn't the calcium also being used for contraction?
Yeah, absolutely. So that's exactly it. So calcium's your signaling molecule. So if you used calcium to depolarize the cell, you'd have a problem. So if you look at these currents, the numbers should tell you something. So this is -380. And the reason it's -380 is because conduction velocity. So how quickly the action potential travels across the heart or down the neuron depends on the peak sodium current. So if you made that a peak calcium current, you'd constantly be flooding the cell with calcium. And you wouldn't only be causing contraction signaling, you'd also be causing genetic changes, because calcium's an intracellular signaling molecule as well. So the cells have essentially evolved so you can get rapid conduction without using the signaling molecule, which is why you have the sodium channel. All right, so now we have, let's say we have our description for each channel. So we know sodium is N3H. We know potassium is N⁴. And then the calcium current will be something like D times F. And we'll have a whole series of differential equations to describe each of these currents, and then we want to put them all together. So we want to solve those equations simultaneously. And this is what you'll be doing with the Hundredi model this afternoon. You want to solve the voltage, right? So that's what you're interested in, is the action potential. And that's going to depend on the currents, right? So current is going to determine the change in membrane potential. And then the sum of those currents is going to equal all those different, is going to be the current is going to be the sum of all the individual components. So you're going to have a sodium current, a potassium current, a heat current. And then to describe those currents, you have these time-dependent equations. And those, in turn, are going to depend on voltage, right? So you have these interlocking set of equations, but the benefit is that you've quantified it. So even though you have this incredibly complex model where all these variables are coming and affecting each other, you have a very quantitative description so that if you get an unexpected behavior, you can track down exactly where it came from. So the second component that we talked about is, how much time do we have? The calcium cycling. So I'm going to talk about this, and then we're going to do a little bit of homework. Does that make sense? And then, Patricia, you wanted?
I think it's probably more important to work on the homework.
Okay. All right. We'll do that. So let's talk about the calcium signaling, and then we'll work on the homework a little bit. So here are the currents that are in the Luo-Rudy model. You have the sodium current, and the calcium current, and then you have the different potassium current. You also have the calcium cycling. So that network SR is one compartment, and that's the SR that's spread out through the whole cell and is bringing calcium into the SR. Here's your circa 2A, that's bringing calcium into the SR. You have a translocation, and that's just a simple diffusion. And that goes into another compartment, which is the junctional SR. So that's the calcium that's right next to the membrane, and that's going to sense the calcium coming in. The junctional SR is where the calcium is going to come from. And so if you look at the calcium release, this is the calcium in the junctional SR. And you can see it starts at 1.8. So here's an action potential, right here at the front, right here where you see this decrease, and you're going to empty the junctional SR. You're also going to empty a lot of the buffer that's holding the calcium in the SR. The intracellular calcium is going to increase by a factor of 100. So from 0.1 to 1, I think I said 1,000 before, it's 100. And then it's going to decrease as the action potential continues. And then as that decrease is going to be due to bringing calcium back into the network SR, which you can see here by circuit 2A. So you have this dynamic processing of calcium, and the reason why it's important is, one, because we're talking about contraction, and second, because that calcium concentration is going to interact with the calcium channel. So we'll talk about that next class. So, for your homework, we're going to solve the sodium channel. We're going to plot a GB curve and an inactivation curve. And so last semester you learned about the Euler method. And that's essentially you can solve a differential equation by multiplying it by the amount of time that you're stepping. So if you take a small enough step, so let's say we just step from here to here, we can assume that it's linear, right? So if we step from here to here, then we're going to end up all the way up here, right? So if we take a small enough step, we can assume that the first derivative is sufficient to describe the dynamics if you simply multiply it by the amount of time we're stepping, right? So if you just step from here to here, it's going to be pretty accurate. We just don't want to take a huge step. So if you multiply the step times the derivative and add it to the original value, you'll get your next value. And then you'll retake the derivative here, you'll take another step, and you'll get this value. And so on and so forth, as you kind of march along the solution. More modern methods, Runge-Kutta methods, don't just use the first derivative. They actually use a set of derivatives. So you measure the derivative at the beginning, at the middle, two evaluations at the middle, and one at the end. So there's a function called ODE45 in MATLAB that will allow you to use a Runge-Kutta type solver, and you can fairly efficiently step through these equations. And so what you're going to do in your homework is simulate the sodium channel. And so as opposed to the neuronal channel, to simulate cardiac dynamics, you need a slow gate as well. So you have a time constant for M, time constant for H, and this slow time constant is J. And that's a slower component of inactivation. That's going to hold the myocyte at rest. So let's spend a few minutes and see kind of how we'll use ODE45. So let me see if I can pull up MATLAB. I think I have to log into VPN. Let me share my screen.
Where can we find the equations for the channel?
I'll post them,
Okay.
and they're also online. Let's see. Got it. I don't see it coming up. I think I'm going to do it like this. Right? Well, we'll just move it over there. All right, so we have MATLAB. And we'll provide the equations that you need. Let's see if I can make it big. And so these are the equations that describe the Hund-Rudy model sodium channel. You can see they're not beautiful. But basically over minus 40 millivolts, you have one regime. And here's alpha H, beta H, alpha J, and beta J. And under minus 40 millivolts, you have your rates for H and J as well. And then here you have the rates for alpha M and beta M. And so what we want to do is use a function called ODE45. And so to do ODE45, we first need to set the initial conditions. So Y0 is going to equal, well, let's just say M0 is going to equal 0. So it's going to be closed. And we can solve these as well. Let's see if we get to that. H0 is going to equal 0. Or is equal to 1, right? J0 is going to equal as well. We need a reversal potential for sodium. Let's set that equal to 60 millivolts. And then we're gonna set a test potential, so V equals minus 10. So let's say we're doing a GV curve. So now we want to use ODE 45. We want to do TY is going to equal ODE 45 of, and we're going to need a derivative at derivative. So this is kind of nice because it tells you what you need. So you need the function that's going to compute your derivatives, right? So we talked about in the Euler method, you need the derivatives, and it's going to take certain steps to go along there. And we need it for a certain amount of time. So let's make our time span 0 to 10 milliseconds. And then we want y0, which is going to equal m0, h0, j0. There's going to be some options, so we just put a blank. It's going to ask for options here. We don't need any options, so we're going to do a blank vector. And then we're going to pass in our potential to the derivative function. So that's the last one. So these are variables pass into ODE 45. Okay, so this should run ODE 45. So what do we have here? We have V, we have E and A, well, which we don't really need right now, so let's get rid of that. We have M, H, and J0. So the last part that we need is to define our derivative function. So let's do that down here. So we'll do function, derivative. And this whole thing should probably be a function. So let's call this function, I'll post this, so don't worry if you don't get it down. Just gotta pay attention to what's going on. So this is the HRD channel. All right, so now we have our derivative function, and that's going to return the derivatives of all of the state variables. So y prime. So y prime equals the deriv. It's going to take time. It's going to take our y, and it's going to take our voltage. And so we decided up here what our y was, right? So y is going to be m, h, and j. Now I'll also post some resources if you want to read about ODE 45. We need to take y, we need to make it into m, h, and j. So m is going to equal y, this is MATLAB, so y of 1, h is going to equal y of 2, and j is going to equal y of 2. Okay, so these are our three state variables. And now we're going to compute our rates, right? And so now that we have our rates, we need to define our derivatives, right? So dm dt is going to equal alpha m times 1 minus m, which is the number of gates closed, minus beta m times m. And then dh dt is going to equal alpha h times alpha h times 1 minus h minus beta h times h. And dj dt is going to equal alpha j times 1 minus j minus beta j times j. Okay, so those are our derivatives. And if we look up here, what we're sending back from derivatives is y prime. So we have to put all our derivatives in y prime in the same order that we sent them in as y. So we're going to say yp of 1 is going to equal m, yp of 2 is going to equal h, and yp 3 is going to equal j. And then this is a funny thing. It wants a column vector back. And it's going to put it in as a row vector, so you have to do this thing where you send it to transpose. So this apostrophe is just going to take the transpose. It's going to send the column vector back. That's just because that's what ODE 45 expects. So we've given it our initial conditions, and we've given it the pulse we're gonna go to. We've calculated the derivatives for each of the state variable, and that's gonna do all the work for us. So let's do plot of t comma y.
Don't we need to pass the derivatives, not the state variables, like in YP?
So it's passing the derivatives out here.
But
So-
didn't you said YP of 1 to like M, H, and J instead
Oh, yeah,
of DM,
no, you're
DT?
right. Thanks, that would have been kind of crazy. Yeah, this was supposed to be dm/dt. Yeah, we meant to put our derivatives there. All right, now we're gonna plot t and y. Let's see how that looks. We'll save it. And then you can see what they look like. Well, I can see what they look like on my screen over here. And so blue is M, and you can see that it increased the time. You can see J is a lot slower, and it's decreasing the time. You can see H is a lot faster. So now, what we can do is we can calculate the current. So we have M, H, and J. And so, here we go. So now we can calculate the current. So the current, I and A, is going to equal M cubed. Oh, we need to do the dot cubed. Dot times H. Dot times J. This is because we don't want to do like the products of the vectors. We want to multiply each individual element individually. Times V minus E and A. So now we need E and A. So E and A equals 60 about. And now we can plot T against I and A. So let's run that. Oh, we have to do this again, right? So it gave us back Y, so we have to tell it what its what Y is. Let's see where the plot went. This is tricky because it's not. Oh, that's kind of interesting.
It's only on the single voltage, right?
No, that shouldn't matter. It should be each of these all multiplied. We can do it. Let's see. Let's figure out what's going on. Oh. No, that should work pretty well.
Is it regular multiplication for the V minus DNA?
Yeah, because that's a scalar. Right, so that's a good question, though. I'm kind of wondering why it's giving us. Oh, I know why. we didn't put vectors in here, right? So we just said y of 1, just giving us the first one. So we want the whole vector here. We want colon comma 1, colon comma 2, colon comma 3. Right. So this is giving us. Are you guys familiar with MATLAB scripting? Right? Oh, good. I'm glad I see people nodding. So basically, no. So basically, we want the whole column. So if we want the whole first column, we need to say all the rows, which is colon of column 1. And then we want all the rows of column 2 and all the rows of column 3. So that's why. Hopefully, it wasn't working. See if I can find it again. Yep. So now we got a nice sodium current. So now you can see exactly how you would compute the GV curve, right? So you'd set it to different potentials, and you'd or the IV curve, right? So you set it to different potentials, and you record the peak currents. And if you want, where'd my mouse go? There. And if you want the conductance, then you just simply do GNA is equal to MQ J, right? So this is GNA, right? Because we divide out this part to get the conductance. And so the one last thing I want to tell you before you go is you need to find the steady state, right? So we cheated a little bit. And we just decided that steady state was non-inactivated and all able to open. So all of them closed and none inactivated. So what we need to do is find the steady state. And so to find the steady state, we need these equations down here. So we get our alphas, our betas, and we're going to make a function called find steady state. Find steady state. That's going to be a function. And that's going to take in voltage. So if we paste in all our equations here, you can make another function to calculate your equation. You're going to compute alpha, and we're going to return three variables. We're going to return m infinity, h infinity, and j infinity equals find steady state. And so m infinity is going to equal alpha m divided by alpha m plus beta m. And we had this equation in the slides if you want to look at it. It's just part of the solution for the differential equation. We have h infinity is going to equal alpha h divided by alpha h plus beta h. And j infinity equals alpha j divided by, alpha j divided by alpha j plus beta. So these will give you your steady state values. We'll pass them back here, and now instead of this, we'll say M0, M0, H0, and J0 equals find steady state of minus E, or let's say minus 150 if we're going to do an inactivation curve. All right, so those are the major pieces, right? So what I want you to do is use ODE 45 and actually simulate the current that's in the 100 model. And then I want you to plot those GD curves and inactivation curves. And it's fairly painful. I know you don't love MATLAB, but knowing how to simultaneously solve differential equations is one of the most valuable things I can teach you. So it just keeps coming back. It's one of those life lessons for engineering.